Okay, so in this lecture we'll look into power management for display and camera. Um, so, so we know that our cell phone, mobile phones or tablet PCs, most I mean all of these devices they have display, and these days you find two types of displays which are most commonly used. One is your LCD, other is your AMOLED, where LCD is liquid crystal display and AMOLED is active matrix OLED or organic LED. Okay. So, in case of LCD, this left hand side is showing a different layers of your LCD display. So, it is not only just liquid crystal, but this liquid crystal is sandwiched between too many layers, and since it uses multiple layers, so you can see here it has a polarizer, color filter which is nothing but glass. Then your liquid crystal comes, then you have a TFT which is your again the glass, TFT is your thin film transistor. Then you have a polarizer, so polarizer is put on both the sides, and then you have backlight unit which are nothing but white LED. So you can see like so many layers are here. And there is one more layer which is not shown here. After backlight you have a, so it's part of backlight itself, that is called diffuser actually. So your LEDs are like a spotlight, more like a spotlight, but we require a uniform distribution of the light in display, just like your tube light and bulb. So tube light, I mean the whole tube is nothing but diffuser, but inside that you will find the bulb. So bulb this basically the outer layer or this cylindrical layer acts as a diffuser, and the same thing happens here. So you will find a rectangular white piece here where you throw the LED light. So on both sides you will have LEDs or one side, and it will diffuse the light and it will get uniformly distributed in your display, so that you see a uniform brightness actually. Otherwise, if you do not have a diffuser, what would happen? You will see a spotlight, like one corner may be white, other may be less light, so it will not look uniform and display will be very bad. Which resolution? That depends on how many basically this each liquid crystal is nothing but acts as a pixel.
So what would be the spatial resolution, spatial density of LCDs?
So they are different depending upon the size. You have like I mean X and Y. Okay, so one side you may have like 1048 or other side you may have a double 2x. So whether you have a 2:1 ratio, it all depends on aspect ratio. So but when it says, most of the time what happens, how many pixel you have in you can say per inch or total size of the display, that is how they define. When they say like some x into y or a number of pixels, then that means in x direction you have that many pixels, and so if you look at the cell phone display specification, it will tell you the resolution actually, and bigger the display, more those numbers will be. So which does not mean that your resolution is higher. For the same resolution, if you have a bigger display, then you need more pixels. I mean this is like a roughly 6-inch display. So I mean these days these displays are coming like some 1000 pixel in x direction and 2000 pixel on. You mean the size? Size I cannot exactly tell actually. Yeah, I mean you can calculate the size of pixel. So that's not difficult. You know the size and divide by number of pixels, you will know what will be the size of each pixel. So on the right hand side, it's your OLED, organic LED. So here your number of layers are much less, and mainly because of the reason that it does not require any backlight, because this is LED, so LED has its own light, so it does not require any LED. So your whole backlight unit is gone, and the backlight unit thickness is significant actually. If you look at the total thickness of your LCD panel, the backlight unit will have huge contribution in that thickness. So once you take that out, the thickness will automatically reduce. Then other layers are also there, like polarizer is not required here. Okay. So two layers we are using polarizer. I mean, in the one side here you are using on the both sides. So and then organic LED itself is very thin actually. So thickness is quite low. It can be as thin as paper actually, and that's why when we talk about foldable displays or flexible displays, you can see those displays are only possible with OLED, not possible with liquid crystal or LCD. So this is how your LCD works. So what you have, this is your liquid crystal. You can see these small like cylinders here, and their alignment is changed or orientation is changed when you apply or remove the voltage, or you apply a different voltage actually. So depending upon how much voltage you apply between the two, its alignment will change. So they will twist actually. So what would happen, let us say you apply a full voltage. When you apply a full voltage, they will twist by 90 degree, and these polarizers are placed with 90 degree orientation. So this is horizontal and this is vertical, which means if I am throwing a light, so if let us say left hand side is your backlight, now when you throw a light from this side, so the light beams will be horizontal. Okay. So now if this liquid crystals orientation is also same as your polarizer, what will happen? It will guide the light in the same direction. Okay. And now these polarizer on the right hand side are vertically placed, so it will block all the light, and what you will see, all black in the output. It will pass some light, but very minimum light, because this polarizer will not block 100%, and that is why sometimes when you do not have any picture but display turns on, you will see a grey kind of display, greyish, not pure black. So that's why it happens, because you turn on the black light, but your liquid crystal does not allow all the light to pass. So liquid crystal is saying, okay, this is a black, but it is not a true black, because some of the backlight is passed through this polarizer, and which appears, and we see a grey color instead of true black color. Now if I want to increase intensity, let us say, what will happen? They will orient in such a way that some amount of light will pass, let us say 50%. Okay. So then your intensity will increase compared to your dark pixel, or what we say off pixel, when it's all black. Then if I want to further increase, so let us say I make it completely 90 degree twist. So what would happen? Your light is horizontal, and as this guides, this light is guided through these liquid crystals, what will happen? So they will twist, and by the time it reaches to your polarizer, it will be completely 90 degree oriented, and all the light will be passed through polarizer, and you will see full light appearing at the output. So in between the two, like 90 degree and 0 degree, you can say. So 0 degree to 90 degree, how much orientation these liquid crystals have, and that will depend upon how much voltage you apply. So that will determine how much light you are going to pass, and once you have that in different intensity, now you can have a color filter. So each color, so now you have a 3 different pixels, and so let us say you have a RGB, red, green and blue. So the different intensity and combined RGB will combine and will create millions of color. That's what happens. And so this is how you create different colors. So let us say my RGB provides 8-bit control, 8-bit intensity. So each color has 8-bit intensity, and 8-bit can have a 2 to the power 8 combinations, which means now I have a 3 colors, so I can have 16 million color combinations. And in fact, you can look at your paintbrush, Have you seen use paintbrush? Huh? So when you change the color, you will see RGB. So in the RGB, you can change the number and see the different color will have different combination of your RGB. The same thing happens here also. So with using this RGB, you can create millions of the colors, and that's how you get a color picture. So this color filter is used in your color display. If it's a black and white display or monochrome, then you don't require this color filter. Okay, so and when all the pixels are off, then you will get black, and then intensity will change as depending upon how much these crystals are oriented, and that will basically depend on the voltage you apply, and then you create different colors. So here is a small video which I want to show. This will tell you how exactly this works.
Today's modern LCD technology is based on a discovery made by engineers Lehmann and Reinitzer around 120 years ago. Let's take a look at the technology in detail. In liquid crystals, the molecules are similar to long, drawn-out rods. As with crystalline structures, these molecules exhibit a strictly ordered crystal structure. The ordering of the molecules creates a directional orientation. In most LCD displays, the liquid crystals are embedded between two glass plates rotated by 90 degrees. This formation produces what is known as a twisted nematic LCD.
So that's what I was talking about there, 90-degree orientation.
A polarization filter is fitted onto each of the outer glass plates. These polarization filters mean that only one dispersion direction of multiple light waves emanating from a light source is allowed to pass through. The light follows the rotation of the molecules and, twisted by 90 degrees, hits the outer polarization filter. As the rotation means that the direction of the light matches that of the polarization filter, the light can also pass through this filter and brightens the outer glass plate at that point. If an electrical field is then generated between the glass plates, the special property of the liquid crystal molecule becomes fully apparent. As the molecules are dipolar, they react to the electrical field and are repelled. The rotated molecule structure is interrupted. When light then passes through the first polarization filter and follows the direction of the molecules, this hits the outer polarization filter and cannot pass through it. When a matrix is created from a number of these individual cells, it becomes possible to display graphics and images. To generate more colors, each pixel is divided into 3 subpixels. Color filters are placed over these subpixels in the colors of red, green, and blue. By triggering the subpixels differently, additive color mixing can be used to generate each color required.
So in reality, in one color pixel consists of 3 different pixel or liquid crystals, and that is called subpixel actually. So that makes you one single color pixel because it has a RGB. And these pixels are so tiny, even these 3 combined pixel will appear to us as a single color pixel actually. Okay, so there is one more display called RGBW. So we already know that red, green and blue is required. So if I want a white light, then I have to turn on all the 3 pixel, red, green and blue. So which means I need to turn on 3 pixels. Okay. But if I add a white pixel, then instead of turning on all the RGBW, I can simply have a one single white pixel, and white pixel you can think of, it's nothing but a transparent. Okay, because we already have a white light, the backlight is nothing but it's a white light, and it is passing through a through color filter which has red, green and blue color. Now if I put another layer of I add another basically layer in the in this filter which is transparent actually, so it will pass all the white light. So now if I want a brightness, and we know like this display have a brightness control. So instead of turning on all the 3 color pixels at full brightness, I will reduce the brightness of my RGB and I will turn on this transparent pixel. So, what will the advantage is here, with the less current you will achieve same brightness, or with the same current you can achieve more brightness. So, that is the advantage here. So, this picture is showing the power consumption actually. So, this is your conventional LED without your white pixel, and once the moment you add a white pixel, you can see for the same brightness it consumes 40% less power. So, this left hand side picture is RGB, this is RGBW with white pixel actually, and both pictures you can hardly differentiate between the two. They have the same brightness, same quality, but this white magic or RGBW is consuming 40% less power. So, that is a huge advantage. So, this was taken from Japan Displaying, JDI, which basically manufactures these displays. So, LCD pixel driver. So, as we know, like this display consists of multiple pixels, and each pixel is driven individually with your TFT, which is thin film transistor, and that act is nothing but switch. So, when you turn on this switch, what will happen? You are applying a voltage across this crystal and it will change its orientation. So, this is a row and column. So, row will basically drive the gate, which will basically turn on and off, and on the column you apply the voltage. So, basically at the drain of this, you can say if it is if it is NMOS, then whatever voltage you want to program this pixel with, you apply that voltage. Yeah, it's nothing but similar to your MOSFETs, but these have a much higher drive voltage actually. They can go 15-16 volt. So, they require both positive and negative. Okay, so what you have actually, you have a column driver IC, and then timing control, gamma references, whole thing is integrated into a display driver IC. That is what we call display driver IC, and this display driver IC receives the data from your processor, which sends you the image data actually, or display data what needs to be displayed, and then our power supplies are generated into DC to DC power converters. So, it is a complex actually IC here, which is used for display driver, and it has so many pins, because you can imagine like you are driving a display actually, so many TFTs, and each TFT corresponds to one pixel, and you know the number of pixels, like there could be millions of pixels. So, you can imagine how many columns and rows will require. So, and most of the time this display driver IC is part of your panel. So, in the panel you will have a LCD, you will have all your backlight, your polarizer, everything, and then everything will be mounted on a board, and on the same board you will have this display driver IC mounted, and which will connect to your main board, which basically main board on the phone through your display cable, which is a flex cable. So, in case of AMOLED, as I mentioned earlier, that since it is LED, so it does not require any backlight, and so there could be color LEDs, or also these LEDs could be white LEDs, and on top of that you can put a color filter. So, just like here in this case. So, this is your LED, but here I have shown 3 different color LEDs, but it is quite possible that you can have all the 3 white LEDs, and on top of that you can put color filter. So, the cheaper AMOLED, basically these OLED displays are made using color filter and white LEDs instead of having a color LEDs, because that is more expensive. And the another thing is, like different color LEDs require different drive voltages, because their forward voltage is different, not same. So, it becomes quite complicated to drive those. So, the same concept applies here. Since it is a LED, so instead of voltage you apply current here, and LEDs require constant current, and the relationship we know these diode have a exponential relationship, and it is required constantly. So, voltage has to be very precisely controlled here, So that's why we instead of a voltage we derive it directly with the current. So you can think about this is this gate voltage is coming from somewhere else, which is basically converting this voltage, or you can say mirroring this current into this FET. So same you have data and rho, and data is nothing again the voltage which you are applying to the gate, and then this voltage will determine how much current is flowing into this LED. So based on the current you are applying into this LED, your brightness can change, and you can achieve different brightness by simply controlling this current. So just like in case of LCD, the orientation was changing, and that was depending on different voltage you apply. So you can get different brightness or intensity. Here, in order to get different brightness, you change the current. So again the same thing, you can apply the RGB concept here also. So you can have red, green, blue and white LED. If you are using color filter, then you can have a transparent dot or pixel, and that will give you again 4, and you can save again some power here. So if we talk about power management for LCD, so these are the different supply voltages which are mostly required for LCD panel, and these specs are mostly for cell phone, not a bigger panel actually. So you require digital supply which is 1.8 volt, analog supply 3.3 volt, then this is TFT row gate drive which is positive 15 volt, then negative gate drive voltage is minus 10 volt. So and then VCOM, VCOM is nothing but the common voltage where other side of your liquid crystal. So the voltage across the this crystal, liquid crystal will be the voltage you apply minus this VCOM. It could be 0 also, but due to some reason this VCOM may be a variable and can be adjusted, because on an average the current voltage you are applying through LCD should be 0 actually. So most of the time what we do, we apply both positive and negative in such a way that average is equal to VCOM. So if your VCOM is 0, now if there is a difference between positive and negative voltage, then average won't be 0. So what you do, you adjust your VCOM to bring to the same average. So the on an average voltage you have applied across crystal remains 0. Otherwise you will get a frozen picture and your display can damage actually. So that's a requirement for the panel itself. Then you have two voltages, 5.5 and minus 5.5 volt, and then you have backlight supply which drives your backlight LEDs. It could be anything. VCOM is not switching. It depends on refresh rate. So if you have a, let's say 50 hertz refresh rate, depending upon how many pixels, so each pixel is basically you have to cover all the pixel within one cycle of 50 hertz. So you can just multiply with the number of pixel and you can see what clock rate you will require, the refresh rate. So that's why this capacitor which is required here, this C or again this C storage, they should be big enough to store or hold your charge for that, because if this capacitor leaks out, then your display basically will change and your whole picture will get distorted. So that's why more refresh rate will give you maybe a better picture quality actually, and that's why now newer displays are coming at like 100 or 120 hertz kind of almost 2x of what regular display has refresh rate. Other thing is like 50 hertz. So even if you, let's say you have some variation, so 50 hertz can be easily seen by our eyes, but 120 hertz will hardly be seen actually. So more you have actually refresh rate. So even if let's say your capacitor leaks out little bit, but and that will basically look like a flicker to our eyes. When your display is changing, then it's nothing but flicker. The brightness is changing. So if brightness is changing at 50 hertz, then our eyes can see but as you keep on increasing the frequency, then even if it's flickering, our eyes cannot see. Yeah, because our eye is more like a low pass filter, so beyond certain frequencies, if you go to order of kilohertz also, then we can hardly see. So if you closely look at your tube light, you can see little flicker. But if you have a, let's say, LED light and you turn on and off at a very high rate, 1 kilohertz, then it will appear like a constant light. And simply by changing the, and that's how we, when we talk about how you change the control the brightness of LED, we'll see the same concept is applied here. So you turn on and off at such a high rate that our eyes will see a constant, but by changing the duty cycle, you can change the level of brightness. So this requires much higher voltage, 28 volt if you are using 8S2P. 8S2P means 8 in series and 2 in parallel. So 2 strings of 8 LEDs connected in series. So total 16 LEDs. You can have a 4S4P also, which means 4 in series and then 4 of them connected in parallel. So you require lesser voltage. So, but since the power consumption will be same, so lesser voltage means now you have a 4 LEDs, 4 strings, so that your current requirement will increase. So these 3 supplies and the other supplies which are not highlighted here, they are mostly part of your DDIC or display driver IC, and these are part of PMIC, these 3 supplies, 5.5 volt, minus 5.5 and this backlight. So they come from your power management IC, or there may be a dedicated power IC for this also. So let's see what all supplies it requires with what current. So what we have, we know everything needs to be generated from your battery, lithium ion battery. So we require 5.5 volt, which is more than your battery voltage. So it requires a boost, and we have positive boost converter. Then V backlight is 28 volt, and each string requires roughly 20 milliamp max current. Sorry?
What's the average load current?
That's what I have mentioned here, 28 volt, 20 milliamp. Okay, so each string, so if you have a 2 strings, so the total current will be 40 milliamp. But you will be boosting your 3 volt to 28 volt, so you can imagine the duty cycle you require, and that 40 millivolt will get boosted and your inductor current will be very high actually. So that is your white LED boost converter and driver, which generates 20 volt and 20 milliamp per string. So that's basically load current requirement for your LEDs, white LEDs. Then we require minus 5.5 volt, 50 milliamp, and that comes from negative buck boost converter, or you may use charge pump also. Charge pump means like capacitive switch capacitor. And everything is here controlled by, so when I say this display has DDIC inside it, the panel actually. So some control signal may come from your mobile processor, and some may come from your display driver IC. Your display driver IC knows when the data is coming from the processor, and it can basically command this display supply driver when to turn on, when to turn off, or if it wants to change the voltage. You can program the voltage also, but most of the time the programming is done through mobile processor over I2C controller serial interface. So, but when to turn on and off, or which one to enable first, which one to enable later, that command comes from your display panel. So there are some power up, power down sequencing required for this display, and these specs come from your display panel itself. So whenever you are designing these power management ICs for display, you need to first look at the display spec, what it requires, and if you want to cater to multiple displays, then you have to make all these timings and voltage, everything programmable, so that you can program in the software based on that one particular display requirement, so that you don't have to design this power supply again and again for different display. So the same PMIC can be programmed to cater to display different display panels. So what would happen, your ABDD AEV, which is plus 5.5 and minus 5.5 volt, that will be turned on first, and you have some non-overlap time which is required by this non-overlap time is required by the display. If you don't meet this, then there is a risk of damaging the panel itself. So that's why they require, and this could be 2 millisecond to 10 millisecond, anything in between. So your 5.5 volt will turn on first, okay, and then minus 5.5. So and then at the end you will have your backlight on. So the reason is, unless this guy comes, you don't want to display your image. So your let's say data image is coming, image data is coming from your processor. So data is collected by DDIC, okay, buffered by DDIC, and now it depending upon what data is there, so that data is nothing but it will turn on which pixel to turn on with what intensity, that will create your image. So that's a data which is coming from your, and that will be driving your this driver IC to tell like how much voltage needs to be applied, okay. And when you start turn on your panel or turn on your mobile, which supply will come first. So this AVDD AV is required first in order to display any image. So but let's say if this hasn't come, which means I cannot display the image, and I turn on the backlight display, what would happen? You will again see that gray display actually, or gray image, and that will be a very bad experience to any user. So when you turn on your mobile and all of a sudden you see your display turned into a gray color, okay. So the moment you turn on, you should right away start seeing some image appearing, and that's why when everything is set, all image data has come, all the supplies are settled, at the end they will turn on the display backlight, and you will see the correct image appearing at your on your display. And when you are turning off, again you want to do the same thing. You want to turn off your display first, because that has turned on at the last. So you want to turn off that before, and then you turn off your negative supply and then positive supply.